All right, folks, here in section 10.7, we're going to get two more tests for us to use to analyze infinite series, the ratio test and the root test. So we're going to round out our weapons used to determine convergence or divergence of series in section 10.7. The first one we're going to look at is called the ratio test. Folks, I cannot stress how important the ratio test is. It is extremely important, and it's very, very powerful. The ratio test is going to be used frequently in the next chapter when we start to look at Taylor series and Maclaurin series. So make sure you understand the ratio test inside and out. The ratio test is actually a type of comparison test. Remember, right now we know the direct comparison test and we know the limit comparison test, but both of those comparison tests required us to go out and find a series to compare it to the given series. Well, the ratio test is a comparison test that actually allows us to compare a series to itself. Really powerful. So here it is. Here's the ratio test. The series a sub n is a series with non-zero terms, and we're going to define p to equal the limit as n goes to infinity, absolute value a sub n plus 1 over a sub n. So immediately, a sub n plus 1 over a sub n, we're looking at successive ratios of the series. And absolute value, well, we're going to have absolute convergence built into the ratio test. So there are three parts to the ratio test. If that limit p, p is the limit as n goes to infinity, absolute value a sub n plus 1 over a sub n, if that p is less than 1, then our series converges absolutely. If p is greater than 1, then the series diverges. If p happens to equal 1, then the test is inconclusive. It tells us nothing. We have to do something else. Okay, my personal notes I have that I made many years ago. I discovered the ratio test was really, really good for series that involved exponentials or factorials. So let's look at an example. Part A, the series n equals 1 to infinity, n over 2 to the n. I see an exponential there, 2 to the n. Part B, you have the series n squared times 2 to the n plus 1 over 3 to the n. So I see some exponentials there. And then part C, nothing screams ratio test, quite like the series n factorial over n to the n. We have factorial and we have exponential, or that n to the n, sometimes we call it super exponential, or the tower function. But you know the drill. Make sure you have these examples written down because it's time to head off to the chalkboard and work through the examples. All right, folks, here in this example, we're asked does it, converge or diverge? And the first series we're given is the series n equals 1 to infinity, n over 2 to the n. So when I see this, I'm seeing an exponential, a 2 to the n. I'm thinking ratio test might be a good test to crank this through. So the ratio test. Remember, we're going to define p to be the limit as n goes to infinity, absolute value a sub n plus 1 over a sub n. And that gives us the limit as n goes to infinity, absolute value. Okay, a sub n plus 1, that'll be n plus 1 over 2 to the n plus 1. And then divided by a sub n, and so I'm going to rewrite that immediately as multiplying by the reciprocal. And let me show you what I do. I'm just laying the foundation for what's going to be coming up, especially in the next chapter. I like to look at this, and I can multiply those two fractions together, and then I could split them apart however I want. So here's how I rewrite any fractions I see in there. I get like pieces with like pieces. What do I mean by that? I write 2 to the n over 2 to the n plus 1. I write that down as a fraction. And then I have times n plus 1 over n. And I do that because I can now, well, it helps me do a little bit of simplifying. 2 to the n plus 1 over 2, or 2 to the n over 2 to the n plus 1. You know, remember 2 to the n plus 1, you can think of that as being 2 to the n times 2, or you can think the bases are the same and we're dividing, subtract the exponents. So n minus the quantity n plus 1 would leave you with a negative 1. 2 to the negative 1 is 1/2. This fraction reduces to 1/2. This fraction, I would divide everything I see in the numerator and denominator by n. And I think I can now do the limit. The limit as n goes to infinity of 1/2, well that's 1/2. The limit as n goes to infinity of 1 is 1. 1 over n is 0. Denominator is 1. So I have 1/2 times 1. So I have the absolute value of 1/2, which is 1/2. 1/2 is most definitely less than 0. So our conclusion, this series, it converges absolutely. Remember, if it converges absolutely, it has just regular old convergence as well. The ratio test tells us that series converges absolutely. All right, B. Looks like a good candidate for ratio test to me because I see an exponential 2 to the n plus 1 in the numerator. I see an exponential 3 to the n in the denominator. So let's crank this through the ratio test. So P is equal to the limit as n heads off to infinity, absolute value a sub n plus 1 over a sub n. So that's the limit as n heads off to infinity. See, a sub n plus 1. Oh boy, that's an n plus 1 squared. 2 to the, okay, n plus 1 comes in here for n, so I'd have n plus 1 plus 1. So that's an n plus 2 over 3 to the n plus 1. Divided by a sub n, so divided by a sub n, so you know I'm going to rewrite it as multiplying by the reciprocal. So 3 to the n over n squared 2 to the n plus 1. Oh, just enough room to get the absolute value in there. So as I showed you in the last example, I kind of got into this habit many years ago of rewriting the mess inside absolute values as fractions that have like parts with like parts. So for example, here's a 2 to the n plus 2, down here's a 2 to the n plus 1. So I write the fraction 2 to the n plus 2 over 2 to the n plus 1. Then I have a 3 to the n up here over 3 to the n plus 1. So I make that fraction 3 to the n over 3 to the n plus 1. And then I'm left with an n plus 1 squared over n squared. All right, so now time to do a little simplifying. Okay, 2 to the n plus 2 over 2 to the n plus 1. Bases are the same. I'm dividing, subtract the exponents, and I believe that leaves me with just 2. 3 to the n over 3 to the n plus 1. That'll simplify down to a 1/3. Now this n plus 1 quantity squared over n squared. I can use another old property of exponents and rewrite that as n plus 1 over n, all raised to the second power. So one more little step. Inside the parenthesis, I'm going to go ahead and multiply that together to get 2/3. Inside the parentheses here, I'm going to come in here and I'm going to divide, actually I'm not going to divide everything in the numerator and denominator by n. I'm just going to say, hey, I have a common denominator of n, so I can look at this as n over n plus 1 over n. So n over n is 1 over n, that quantity squared. So folks, as the limit as n goes to infinity of 2/3, we know that's 2/3. We know the limit as n goes to infinity of 1 over n is 0. 1 plus 0 is 1. 1 squared is 1. So we have this limit to be absolute value of 2/3, which is 2/3, which is most definitely less than 1. And according to the ratio test, when this p is less than 1, our conclusion, I'm going to write the conclusion up here because I'm running out of room down here. Our conclusion, the series converges absolutely. Oh, and you know, I should be giving a reason. Converges absolutely via the ratio test. Now, I should have said that here as well, that this converges absolutely via the ratio test. All right, so let's see. I thought there was a third part to this example. Oh, there was. The series, let me erase the board, get part C up here. The series was, it was a series that absolutely screams ratio test. So, let me erase all this because I might need a lot of room. The series n equals 1 to infinity n factorial over n to the n. So that was part C of this example. And again, I say this one screams, it absolutely screams ratio test. We have factorial and we have exponential, or as some of us like to call it, super exponential. Ratio test. So we start off with our ratio test. P is the limit as n goes to infinity. Absolute value, a sub n plus 1 over a sub n, which equals the limit as n goes to infinity. Absolute value of, n plus 1 factorial over n plus 1 raised to the n plus 1 times, that would be n to the n over n factorial. Now I'm gonna rewrite this. I'm gonna rewrite it, getting all the little like pieces together. So I have the limit as n goes to infinity, n plus 1 factorial over n factorial times n to the n over n plus 1 to the n plus 1. Okay, so the first thing I'm going to look at simplifying here is the factorials. The n plus 1 factorial over n factorial. And let me go way over here to the side. I know we discussed this early in the chapter, the factorial notation, but let me bring that over here, that your n plus 1 factorial over n factorial. Well, remember what factorial means. N plus 1 factorial means n plus 1 times n minus 1, yada, 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 3 times 2 times 1. N factorial means n times n minus 1 times n minus 2, yada, 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 3 times 2 times 1. So really, n plus 1 factorial means n plus 1 times n factorial. And those n factorial, they will cancel out. So that just simplifies to n plus 1. So we've simplified this fraction. So let me pull the problem up here. we've simplified this fraction and it simplifies to n plus 1. All right, now a neat thing happens. You have an n plus 1. Down here you have an n plus 1 raised to the n plus 1 power. So you should be able to simplify n plus 1 over n plus 1 to the n plus 1 power. I mean, remember, we're talking about basic rules of exponents. When the bases are the same, n plus 1, bases are the same, and you're dividing, you can subtract the exponents, and that leaves you with the limit as n goes to infinity of n to the n over n plus 1 to the n. Which, you know, I'm going to rewrite that using a rule of exponents. N to the n over n plus 1 to the n, I'm going to write that as n over n plus 1, all raised to the n power. Now, we have seen something that looks like this in the past when I showed you about manipulating things with a negative exponent, how to get what's in the parentheses to flip, how to make that the denominator and make that the numerator. So this was in a previous video, but basically n over n plus 1, I can write that as n plus 1 over n to the negative n. And then once I write it as that to the negative n, I can say, well, this is the limit as n goes to infinity of 1 over n plus 1 over n to the positive n. And I'm pulling the beastie up here. The limit as n goes to infinity, absolute value. Now look inside the parentheses here. You know, that's just a 1 plus 1 over n. 1 plus 1 over n to the n power. We should know immediately what this limit is. I mean, the limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 1 plus 1 over n to the n power, well, that limit is e. So we get 1 over absolute value of e, which is 1 over e, which is most definitely less than 1. Conclusion, our series converges absolutely thanks to the ratio test. So that was it for that example. And there are a few problems I'd like you to do. So let's see. How about doing numbers here in section 10.7? Let me write them over here. 10, 14, and 21. So go ahead, pause the video, go do numbers 10, 14, and 21, and when you're done with those, I'll be here at the board working them out. All right, folks, here number 10, you were asked to determine if the series n equals 1 to infinity, negative 2 to the n over n factorial, if it converges or diverges. It looks like a great candidate for the ratio test. I see an exponential and I see a factorial. But before I get started, I want you all to realize that this series can be rewritten. I mean, look inside the parentheses here, negative 2. Negative 2 is nothing more than negative 1 times 2. Then a rule of exponents says if this is negative 1 times 2, all of that raised to the nth power, I could think of it as negative 1 to the n times 2 to the n over n factorial. So I just wanted to show you that you could rewrite it. Now that means absolutely nothing in the fact of using the ratio test. It's just something important coming down the road. I know what's coming down the road, and it's important that we can see these two are absolutely the same thing. Why it doesn't matter for the ratio test is that the ratio test, you're doing the absolute value of a sub n plus 1 over a sub n. So it doesn't matter if you call this whole thing a sub n, or you just call the 2 to the n over n factorial a sub n. It doesn't matter, because when you're doing the absolute value of that negative is going to be what's going to be positive. So let's get on with it. Let's see, a sub n plus 1. Well, a sub n plus 1, that gives me a 2 to the n plus 1. N factorial is n plus 1 factorial. Then times n factorial over 2 to the n. And, well, I put that step in of putting all the like pieces together. So I have 2 to the n plus 1 over 2 to the n times n factorial over n plus 1 factorial. So let's see, 2 to the n plus 1 over 2 to the n. Well, that leaves me with a 2. Okay, n factorial over n plus 1 factorial. Well, remember, n plus 1 factorial is nothing more than n plus 1 times n factorial. So I guess I'm left, the n factorials would cancel out. I'm just left with a 1 over n plus 1. So folks, as n goes to infinity, this is 2. This is 0. 2 times 0 is 0. Absolute value of 0 is 0, which is less than 1. Conclusion, our series converges absolutely thanks to the ratio test. Alright, so I think what I need to do now is I need to erase the board to do number 14. Too much chalk dust. So let's see what number 14 is all about. '14 was the series n equals 1 to infinity of n to the n over 2 to the n. Okay, folks, I don't have a good feeling about this one converging, because the numerator is the super exponential or tower function, whatever you want to consider it, and it grows. It's the fastest growing function that we've seen so far. It grows faster than the exponential 2 to the n. But let's go through the process of using the ratio test. This is just practice using the ratio test. I know what my gut feeling is saying. So let's see, ratio test. You have the limit as n goes to infinity, a sub n plus 1 over a sub n. So that's the limit as n heads off to infinity. N plus 1 to the n plus 1 over 2 to the n plus 1 divided by a sub n, so I multiply by the reciprocal. Then let's get my fractions together that have all the like looking pieces. So 2 to the n over 2 to the n plus 1. And then an n plus 1 to the n plus 1 over n to the n. So now we have the limit as n goes to infinity. Let's do a little simplifying. 2 to the n over 2 to the n plus 1. That should simplify down to 1/2. And then we have n plus 1. Oh, let me write down. That's all we have. N plus 1 to the n plus 1 over n to the n. Okay, it's looking like we're at a dead end, but we're not. Rules of exponents always come in handy. This numerator, n plus 1 raised to the n plus 1. Well, I can think of that as n plus 1 to the n times n plus 1. I mean, when the bases are the same and you multiply, you add the exponents. So I'm just taking advantage of that rule of exponents to rewrite it as, rewrite n plus 1 to the n plus 1 as a product. And I'm doing that because let me just leave this n plus 1 here. I can rewrite that. Thanks to a rule of exponents, I can rewrite it as n plus 1 over n to the nth power, which you know and I know. The n plus 1 over n, I can write that as 1 plus 1 over n to the nth power. So let's see, the limit as n goes to infinity. Well, the limit as n goes to infinity of 1/2 is 1/2. The limit as n goes to infinity of 1 plus 1 over n to the n, we know that limit is e, so we have a 1/2 times e, but the limit as n goes to infinity of n plus 1, that is infinity. So a 1/2 times e times infinity, this limit is infinity, which we know is most definitely larger than 1. So our conclusion, the series diverges thanks to the ratio test. I encourage you all, if you've noticed how I've done the 3 examples, and this is the second homework problem, if you've noticed how I've done each one of them, I've started off by writing down the ratio test. We are defining P to equal the limit as n goes to infinity, a sub n, absolute value, a sub n plus 1 over a sub n. I encourage you to do that and get into that habit and following down the string of equals, because what I've really done here at the very end, it's P is equal to infinity, and the ratio test says that if P is greater than 1, the series diverges. So I encourage you all to get into that habit. I know what's coming up, so get into the habit now. Let's see, there was one more, number 21. Oh, number 21, that's a doozy. Looks kind of fun. You got factorials running all around, getting squared. It's just an algebraic simplification bonanza here. So let's look at 21. Got the series. N equals 1 to infinity. N factorial squared over, a 2n factorial. Wow, we have factorials running around everywhere. Ratio test. P equals the limit as n goes to infinity, absolute value, a sub n plus 1 over a sub n. It's the limit as n heads off to infinity, absolute value. Alright, so a sub n plus 1. That's going to give me n plus 1 factorial, that whole quantity, squared. So n plus 1 factorial, and then I'm going to put that whole quantity inside brackets, squared. And here, the denominator, that's going to be 2 times n plus 1. And then that whole quantity, factorial. Okay, divided by this, so you know I rewrite it as multiplying. So multiply by the reciprocal. Okay, well, now what? Alright, so here's what I think a lot of this comes back to. This n plus 1 factorial. Just knowing that n plus 1 factorial is equal to n plus 1 times n factorial. I think that helps me. So let me rewrite that. This n plus 1 factorial, I'm going to rewrite it as n plus 1 times n factorial. So I'm rewriting this as n plus 1 times n factorial. Then I have to remember all of that is being squared. Why don't I then make the denominator, like I tend to do, I put like pieces together. Why don't I make it this n factorial squared? So then I'm left with the 2n factorial over, alright, so now let me go over here on the side. I have a 2 times the quantity n plus 1, that whole quantity factorial. So I have this 2 times n plus 1, that whole quantity factorial. Well, that, if I distribute the 2, I get 2n plus 2 factorial. Well, 2n plus 2 factorial, let's think about what that means. It means 2n plus 2 times 1 less, which is 2n minus 1 times 1 less. So it would be times 2n times 2n minus 1 times 2n minus 2 times yada yada yada, 3 times 2 times 1. But notice everything that would be after this, the 2n times 2n minus 1, that quantity factorial, times a 2n minus 2 factorial. Notice that is nothing more than just 2n factorial. Sorry, yeah, that should be a plus 1. So I went over there, distributed the 2, got the 2 quantity 2n plus 2 factorial, wrote down what that meant. So I'm rewriting this as 2n plus 2 times 2n plus 1 times 2n factorial. Oh, we got a lot of factorial stuff running around, but let me block this off. Look at the neat stuff that happens. Okay, we have an n factorial that's being squared. I mean, we have an n plus 1 that's being squared and n factorial that's being squared. Well, this n factorial that's squared is going to cancel with this n factorial squared. That's kind of neat. This 2n factorial is going to cancel with that 2n factorial. So look at what you're left with. You're left with an n plus 1 quantity squared that cancels, that cancels, that cancels, that cancels. So I guess the denominator is just the 2n plus 2 times 2n plus 1. That looks doable now. So what I would recommend doing is just good old-fashioned algebra, foiling. N plus 1 quantity squared is n squared plus 2n plus 1. You FOIL out the denominator, you're going to get 4n squared plus 6n plus 2. Divide everything in the numerator and denominator by n squared, and we almost are there. So now it's just time to find the limit. The limit as n goes to infinity. That would be 1, 0, 0, 4, 0, 0. So you get the limit to be absolute value of 1/4, which is 1/4, which is most definitely less than 1. So from the ratio test, our series converges absolutely thanks to the ratio test. Okay, so that's number 21. So you've seen 3 examples, done 3 homework problems, working with the ratio test. So let's head back to the slides to get the final test. It's called the root test. All right, folks, after doing those 3 examples and looking at numbers 10, 14, and 21, hopefully you're getting a good idea of how the ratio test works. So it's time for our final test, the root test. The root test can be useful if you see nth powers. I'll be honest, in the grand scheme of things, I rarely use the root test, but let's look at it for completeness sake. So here's the root test. You have a series a sub n, non-zero terms. We're going to define p to equal the limit as n goes to infinity, the nth root of absolute value a sub n. So again, we have built in here an absolute. We're testing. This test is immediately telling us something about absolute convergence. If this limit p is less than 1, then the series converges absolutely. If p is greater than 1, then the series diverges. And if p is equal to 1, then the test is inconclusive. It tells us nothing. We can make no claim whatsoever. So this example, does the following series converge or diverge? It's the series n equals 1 to infinity of the quantity 2n over n plus 1, all of that raised to the nth power. So, you know, it's time to head off to the chalkboard and work through this, and see you there. All right, folks, our final test is called the root test. And I think I mentioned this in the slide, and I'll mention it again now. I just rarely encounter situations to use the root test. It's almost as if it has to be specially constructed for me to use the root test. So out there in the wild, when I'm running across the series, rarely do I encounter the need to use the root test. But this example is ideally set up to use the root test. So let's remember what the root test says. You define p to be the limit as n goes to infinity, the nth root of absolute value a sub n. So for this one, this is the limit as n goes to infinity, the nth root of, well, it doesn't matter if I had a negative sign in here, like a -1 to the n, or not. When we do the absolute value, we get a positive. So this is my a sub n. So let me write that in there, 2n over n plus 1 to the nth power. So we know when we do the nth root of something to the nth power, we're left with just that. And then if you divide everything in the numerator by n and everything in the denominator by n, you're going to see the limit as n goes to infinity is 2, which is definitely greater than 1. And if it's greater than 1, we know the series diverges. Thanks to the almost never used root test. Alright, so here's a couple I'd like you to practice. One's definitely going to use the root test. The other one, I don't know. So try number 18 and 33 here in section 10.7. For number 18, I'll give you a hint. Remember n squared? N squared equals n times n. Alright, so now go ahead and pause the video, do 18 and 33, and when you're done, I'll be here at the board working through them. All right, folks, number 18, you're asked to find if the series n equals 1 to infinity of 1 plus 3 over n, all raised to the n squared power, if that series converges or if it diverges. And hopefully you saw what my hint was referencing. This exponent of n squared. N squared is, well, n squared is n times n. So this n squared is n times n, which means I can write n times n, that exponent, n times n, as n, and then everything raised to the n power, because of an old rule of exponents. When you have a power raised to a power, you multiply them together. Now it's contrived to definitely crank it through the root test. So the root test. P is the limit as n goes to infinity, the nth root of, the absolute value of a sub n. Well, the absolute value is just this positive thing, 1 plus 3 over n to the nth power, square brackets, to the nth power. So you know the nth root of something to the nth power, you know that's going to just leave you with the limit as n goes to infinity of 1 plus 3 over n to the nth power, which you should immediately know that limit is e cubed. And e cubed is definitely greater than 1. Conclusion, the series diverges thanks to the root test. All right, now number 33. Number 33, that was in that block of exercises that I think the direction said something along the lines of use any test to do this. You know what? I'm seeing just a little bit of playing around might make this an easier problem. Here's what I mean by a little bit of playing around. 2 to the n plus 1. Well, 2 to the n plus 1 is 2 to the n times 2. Rule of exponents. 9 to the n minus 1. Well, that's 9 to the n times 9 to the negative first. I can get rid of this negative exponent by moving it upstairs. It would become 9 to the first. Oops, I left off my n there. So if I move this up here, and it's 9 to the first, look, I'd have a 2 times 9, which is 18. And then notice I have a 2 to the n over 9 to the n. That's 2/9 to the n. Folks, based upon something that I said earlier, this series is the exact same series. I could use properties of exponents. This is the exact same series as 18 times negative 2/9 to the n. Because negative 1 to the n, 2/9 to the n, I could use a property of exponents and say, well, that's really negative 1 times 2/9. Negative 1 times 2/9 all to the nth power. And when the negative 1 times 2/9 is negative 2/9. What's the value in doing this? Why would I do that? Why would I want to see it like this? Or why would I want to see it like this? That's right, it's a geometric series. It's a geoseries. Here I could say it's a geoseries. R is negative 2/9. But go back and look at that geometric series, what we learned about the geometric series. If the absolute value of R is less than 1, we know the series converges. the absolute value of R, the absolute value of R is the absolute value of 2/9, which is 2/9. That's definitely less than 1, which tells us this series converges, and more importantly, it converges absolutely, because it's a geometric series. That geometric series that we learned way back at the beginning of the chapter, it kind of had that absolute convergence built into it already. There's a good reason why I wanted to revisit that. There's a good reason why I wanted to do it, because well, now I'm going to say, you can do the homework in section 10.7. You're ready to go. Section 10.8, there's absolutely positively nothing new in that section. It's just a bunch of exercises where any test is fair game. And that's where recognition, it really hammers home what I said earlier in the chapter, how recognition is really important. But let's not worry about 10.8 yet. Let's get section 10.7 under control. So go ahead, head off to the homework in section 10.7, crank through them, and thanks for watching.